Check it out now, y'all.
nanoHUB-U Online Instruction.
Welcome back. We are talking about selectivity of nanobiosensors. And in the series, you have already heard two types of selectivity issues. And first of all, I have tried to explain very well that selectivity is one of the most important and fundamental concerns for nanobiosensors. Many sensors are highly sensitive and often they can detect molecules at very low concentration. But the reason many of the new technologies never make it is because they are not really selective enough. So today I'm going to talk about a third universal selectivity concern of nanobiosensors, and that has to do with the noise in the transducers. So I'll explain why noise is such a big concern, such a big selectivity problem. And it turns out that it is a concern for all different types of biosensors, be it potentiometric, amperometric, or even cantilever-based. So therefore, this is something that will be present no matter what technology you use. I will explain different types of noise sources that are important. And then, in particular, I will explain the math associated with it, or the physics associated with the white noise and the pink noise. And then, once we describe what the noises are, just like we have done previously, we'll try to see if there is any way to improve the signal-to-noise ratio, or can we suppress the noise somehow so that we can have improved detection and better selectivity. Briefly, you may remember from the previous two slides that when the biomolecules land on the sensor surface, then of course we have the signal term in red. It means the correct biomolecule has attached to the correct receptors and the conjugation is what we're really looking for. But of course, there can be wrong biomolecules attached to the receptor. In that case, that's the blue region. So that's a selectivity problem. And of course, there may be the wrong biomolecules may be sitting in the empty space on the sensor surface itself. That will also produce a noise. That's a typical kind of noise we have talked about. And if you express the fraction of the correctly captured molecule with respect to the total number of molecules captured, biomolecules captured, call that alpha, and call beta to be all the parasitic capture events, then we saw that the biosensor can be described by a small matrix where the alpha on the diagonal, they dictate or they allow you to say what fraction of the molecules are correctly identified, and beta are all the incorrectly sort of identified, false positive associated with this sensor. And so therefore, if you come with 1001, let's say two proteins present and the two being absent, it turns out sometimes you will say that the protein is present while it is actually not. And sometimes you will miss the presence of protein because alpha plus beta is not equal to 1. So in that case, you sometimes may actually miss it, whereas in reality, the protein is actually there. So this is the issue about false positive and false negative that we have already discussed. What I'd like to say now is that there are a few additional terms that contribute to beta. So where do these new terms come from? Where does this additional noise terms comes from? Well, you remember that the whole system, if you look at the entire biosensor system, there are all these red molecules, biomolecules, and different types of biomolecules, let's say in the blood. We capture only a certain one, and of course there can be a false capture. But even if the capture was perfect, no every biomolecule with 100% specificity get corrected with the corresponding capture molecule. And let's say somehow by magic, we could eliminate all incorrect binding whatsoever. Even in that case, the detection will not be perfect. The reason is that there are environmental noises. There will be fluctuation in the fluid itself, for example, that can produce a signal even though there is no molecules present. So that gives you a false positive. Similarly, there will be noise associated with this transducer itself. So for example, we may have captured 3 molecules, but because of the noise source, because of the noise sort of going in the opposite direction, we may report that we have captured only 1. So therefore, both this transducer and environmental noise can lead to false positive or false negative that we really do not want. And I have alluded to this noise problem before and in various lectures. For example, when we are talking about how to beat the Nernst limit, super Nernst sensors, pH-based sensors or potentiometric sensors. In that case, we discussed about these various noises shown here in the red line. And I said that compared to the signal, which is the blue, the noise levels can be different, depend for this type of structure. And similarly, if you look back in the subsequent lectures, we'll see that the genome sequencers will also, in that case, we'll also see that there are certain amount of noise associated with it. And we wrote a formula like this. So today, what I'd like to do is to explain where this comes from. And in that process, then you'll be able to understand probably these things which were not probably very clear in the previous lecture. Let's quickly review that there are 3 types of sensors that we have discussed in this course. Potentiometric sensor that converts the charge of a biomolecule, this yellow biomolecule, to the current of a channel current of a MOSFET. And then there are amperometric sensors. In the amperometric sensors, the chemical affinity associated with the yellow molecule is converted to the current in the circuit through a redox reaction. And finally, the mass gets converted to frequency in the mechanical sensors or cantilever-based sensors. All 3 have noises. What it means that even if the biomolecule were not present, let's say there is no biomolecule, so therefore you should not be detecting anything. The current should be flat, all the responses should be completely time independent. But if you go and measure, then what you will see, even when the yellow molecules are absent, there is a current flow, fluctuating current flow. There is a current flow in the output circuit in here, and there is a irreducible oscillation of the cantilever beam even when it has not captured a biomolecule. So let's see where these noises are coming from. What is the physical origin of these noises? So here I show 5 examples. The first example is, let's look at the entire potentiometric sensor. When the electrons go in and out of the fluid gate, as the electron go in and out, there is a corresponding noise, because sometimes 50 electron will go in and sometimes 48 electron will go in. And then therefore, depending on, because it's never a constant number, it's constantly fluctuating about a mean value. So there is a noise associated with it. We'll call this noise electron noise, and we'll use the symbol A to classify it. So we'll say it's a type A noise. Then if you look inside, although the fluid looks perfectly calm, let's say the salt molecules, looks perfectly calm, pH, hydrogen protons and OH groups, or OH atoms perfectly calm. But if you sort of took a microscope, really small microscope that can see water molecule within a given volume, you will see that the molecules are running around all the time. And sometimes the box will contain X number of particles, sometimes X plus 5 number of particles, sometimes less. And so this would be called an electrolyte noise. And because of the electrolyte noise, of course, there will be corresponding fluctuation in the channel current, right? Similarly, you can have, once the molecule comes in and gets absorbed, it may not stay there forever. It can get dissolved after a while. Remember the Kf and Kr, the association and dissociation rates. So there can be an absorption-desorption noise. That's possible. Now, even if all this top side were completely calm, no noise, even then, this will not be noise-free. The channel will not be noise-free. Why? Because as the electrons are trying to come from source to the drain, the number of electrons, which is shown here in the green circle, and number of holes in a given volume, that number fluctuates because it's interacting with the thermal environment. And finally, as the electrons are coming in, as I'll explain a little bit later, it can be trapped by traps within the oxide. That's shown here in green. So sometimes, let's say 50 electrons are coming in, 3 got trapped, so 47 moves along. And this trapping and detrapping correspondingly leads to a fluctuation and noise. So there are 3 types of noise that we have tried to classify. One is this electrode noise, electrolyte noise, and channel noise. These we'll call white noise. I'll explain why I do call them so. And this type of trapping, detrapping, we'll call it pink noise or 1/F noise. And then, of course, there is a third category, absorption, desorption noise. This, for the time being, we'll not consider further. The same thing happens, of course. Same thing happens for the amperometric sensors. Amperometric sensors of electrolyte. So there's the electrolyte noise, electrode noise, absorption, desorption noise. And of course, as the electrons through the redox reaction, electrons are coming in and out, then there is a corresponding noise source associated with it. Now, if you go back and see for the cantilever, once again, there'll be noise associated with it. For example, if you look at this, there's constant air molecules constantly coming in and bumping across this cantilever. So the cantilever is oscillating like this, even though the biomolecule may not be present. But of course, could be absorption, desorption noise associated with the biomolecule itself. So bottom line is, no matter what sensor you have, there'll be always this fundamental noises associated with the sensor itself. So there are 2 types. This is the top one, what we called white noise, is type A. So if you go and review the previous 3 slides, you will say that anywhere you see type A noise, we'll call that a white noise. And the white noise, you can see, is going up and down, going with a more or less constant amplitude. And the reason it's called white, because this, if you Fourier transform this signal, then you will see equal amplitude for the signal for all frequencies. That's why, just like white noise, white light contains frequencies of various frequencies of equal proportion. Similarly, since this noise contains all frequencies, hence the term white noise. The pink noise is essentially slightly different. This is the spectrum, this is the time spectra associated with it, sometimes very large, sometimes quite low. And if you look at the Fourier transform of it, frequency component, on low frequency, there will be very big amplitude. So you can see very big amplitude there. And in between, the higher frequencies have a relatively lower concentration. Fewer, this amplitude is smaller. So these 2 types of noise, let's see where they come from. White noise is very easy. You see, think about a resistor, and we have added a little capacitor across it. Let's say this resistor has, let's say, 7 electrons and let's say 7 holes. So they are charge neutral, and therefore, let's say there is no charge across the capacitor, because you see there is no battery or anything. So you would think that across the capacitor there would be no charges or no voltage that would be generated. But in general, that's only on average, because sometimes it may happen that certain number of electrons, these blue electrons may sort of go in one side and the white holes may go on the other side, temporarily, statistically. And so what will happen? This terminal will become positive, that terminal will become negative, and so there will be a little bit of positive voltage generated for a transient moment. And then, of course, a little while later, there may be holes on this side, electrons on the other side, and so this terminal will become positive, this terminal will become negative. So you can see if you had a voltmeter across here, it will read sometimes positive, sometimes negative, and it will keep fluctuating around. That's noise. Now, this is how it's going to look like, and it's very easy to calculate what the strength of this noise is. Generally, the energy across this capacitor is half CV squared. Now, this energy is coming essentially from the environment, and therefore it will equate it to kT over 2, because it's 1 degree of freedom, and so therefore in 1 degree of freedom from thermodynamics people say that it will be equal to kT over 2. Let's assume that that's the case. And so you can immediately see that the Vn square will be inversely proportional to the capacitance. But we also know that for a resistor capacitor combination, the bandwidth or the cutoff frequency is 1 over 2 pi RC. Take this C, insert it in here, and you will see that the amplitude of the noise is given by 2 pi, which is something we know. KT, K is a Boltzmann constant, T is the temperature. Let's say we are doing it at room temperature, so 300 degree Kelvin. And resistance associated with it, and the bandwidth. The bandwidth meaning the range of frequencies that we are interested in. Now, if you do a real calculation, instead of 2 pi, which is about 6 or so, we'll have 4. But other than that, if as soon as you know the resistance, other things are very easy to calculate, and you can say how noisy your particular resistor is going to be. Now, often what people do, they want to know per unit frequency what is the noise, and so they will divide Vn square over B, and therefore it's 4 kBT R. R is the resistance, T is the temperature. Okay. Now, what does this resistor has to do with biosensors? It turns out that a lot. For example, if you want to look at this electron coming in and out, for the case of potentiometric sensor, for example, electrons coming in and out of the electrode, in that case, the noise that we'll have 4 kT, but we'll simply replace the R with the contact resistance. That's something you can easily measure. Pump a current through this small electrode, find out what the resistance is, and then you put it in. That will tell you what type of fluctuation to expect from this electrode. Now, what is this? This one is the salt molecules moving up and down, getting in and out of the box, sodium chloride atoms. Again, all you have to do is to replace R, the resistance, with the solution, resistance of the solution. How do you calculate that? Well, you know the molar concentration, and then you know the mobility associated with sodium or chlorine, and from that you can calculate R sol. Put it in, so you know the electrolyte noise. Very easy, you see. And finally, if you wanted to know channel noise, as the electrons were going from the source to drain in the MOSFET channel, once again, all you have to do is to calculate the channel resistance, put it in, there you get the noise. So type A white noise, easy to calculate. Just find out the resistance associated with the corresponding process, and you are done. And then eventually you can add them all up. Now, what about the pink noise? Well, the pink noise is a little bit more complicated, but it's not too complicated. You see, the drain current is proportional to the number of electrons you have and the mobility of the electron multiplied by the electric field. So change in the drain current is, if you take a log on both sides and take a differential, it's proportional to the change in the number of electrons and change in the mobility. So you see what happens, that let's say 3 electrons has started coming in. It comes in up to a certain point and then gets captured by the white trap. So now 2 electrons are going in. So if you look at the number of electrons in that instant, you will see the number of electrons has gone down from 3 to 2. Of course, if it gets trapped farther in, then it's going to stay there longer before it comes back. And so therefore, it will go from 3 to 2, but it will stay there longer before it comes back. So that's the electron number issue, that there will be a fluctuation in electron number, this delta n. Moreover, when the charge is trapped, they are going to scatter the other 2 electrons, which are going on their own way. And that's the change in the delta mu. So once you account for these 2 processes, there will be a corresponding noise, pink noise associated with it. And so people have calculated what this noise is, but I'll just show you how it comes about. Generally, what the general interpretation is that generally if you look at a textbook, you will get a formula like this. It has a 1 over f dependence. Smaller the frequency, higher the magnitude. And the number fluctuation when things get trapped is given by this first factor multiplied by 1. And the mobility fluctuation, because the scattering of the free electrons by their trapped counterparts, is given by this mobility fluctuation. Now, typically for biosensors, alpha would be equal to 1 because we are always in the linear regime. The current is very, very small. And so therefore, all one has to do that if you wanted to know how much noise you have between frequency f1 to frequency f2, all you have to do is to integrate this noise up, and that will give you the total amount of fluctuation that will happen because of trapping and detrapping. See, even though the biomolecules are not producing anything, this noise itself can give false positive or false negative. You can easily calculate these numbers. For example, if you have an oxide capacitance of a certain amount, defect density, the tunneling length into the oxide, you can put these numbers in and you can easily calculate that the noise can indeed be significant. This is V squared is 10 to the power minus 4. So V would be 10 to the power minus 2. So that's quite significant. It's on the millivolt per hertz range. So it can be significant amount of noise. But the most important point I wanted to emphasize is W over L. This is the curse of nanobiosensors, that as you make things smaller and smaller and smaller, the W and L becomes small. And therefore, the noise becomes very large. Because in small structures, you have only a few electrons. So when a few gets trapped, the disruption is more significant, right? That's why nanobiosensors pays dearly in terms of noise enhancement, especially 1 over f noise enhancement. Okay, so this is a fundamental issue, this type of noise. How are you going to beat it? Is there any way, or should we have to live with it? It turns out that there is a very interesting way to actually beat this noise. You see, the noise essentially is contaminating our detection, as I have explained in the last slide. So let me explain to you how we can actually reduce the noise by averaging. You see, if you had a signal S, let's say produced by the biomolecule, and if you had the noise associated either with the electrolyte or with the pink noise, trapping, detrapping, and let's say sometimes it's going positive, sometimes it's going negative, sometimes so there'll be a constant fluctuation up and down. One thing you immediately realize that if you were just measuring one sample, then this S divided by N3, S naught divided by N3, that will be your signal to noise ratio. And anytime the green falls below the N3, then we are done. We cannot detect it. But you see, if instead of just measuring one sample, if the signal was changing slowly, as it often happens in biosensing, and if you can make many measurements, then if you add them all up, because sometimes they are positive, sometimes they are negative, the total noise will go down after averaging. And so if you sum the 5 samples up and then compare with 5 signals, 5 samples of signals, do this ratio, that will be significantly better. In fact, more the number of sample, noise will keep going down and signal to noise ratio will keep improving. And this is essentially the same statement shown here on the bottom. So let me give you an example. For example, here for the white noise we have a spectrum, and for a pink noise, let's say we have a spectrum pretty bad, going magnitude is quite high. But instead of staying with it and being sort of frustrated that the signal to noise ratio is defined by the maximum value of the noise associated with the signal, what we can do that we can take average of, let's say, 100 samples or 200 samples, 500 samples, the window. In that case, as soon as you average it, because it's going up and down, this noise will go considerably, will be suppressed, and the signal to noise ratio will improve. And the same for the pink noise. In that case also, the signal to noise ratio would be considerably enhanced. All right. So let's see, after a proper calculation, how much gain can we expect? So here is an example. The blue line is the white noise. The x-axis is the sample size. Did you average over 20? If you averaged over 20, then it would be at this point. If you average over 500, then this is 100, this is 500, so you'd be at this point. Now, in this case, even if your signal was a factor of 10 smaller compared to a noise, let's say in that case, you wouldn't be able to detect anything classically. However, as soon as you take about 50 to 100 samples, you can see the white noise, essentially, the signal becomes larger than the white noise. And 1 over f noise takes a little bit longer, let's say a couple of 100 samples. But if you do, let's say a couple of 1,000 samples, sample it at a kilohertz range for a signal that is changing on a second length scale. In that case, you can see even if the signal was buried inside the noise, you can have a proper signal to noise ratio and faithful detection of the signal itself. So let me conclude then. I told you about 2 types of selectivities. One has to do with the biomolecule. That was the last 2 lectures. And this one has to do with transducers, which is the noise associated with the transducers itself. Even if the biomolecules were perfect, this noise would remain. Now, of all the noise sources, if you do a proper calculation, it turns out the 1 over f or the pink noise is dominant for potentiometric sensors. Something has to be done. You can ignore all the electrolyte noise and as well as other noise sources, but 1 over f noise is something that cannot be ignored. And so therefore, understanding the noise sources is very important. On the other hand, thermal noise, this white noise, plays a very important role in the cantilever sensing because after all, there is no trapping, detrapping. So in that case, this is not present, and in its absence, the thermal noise becomes very important. Now, because the analyte concentration generally, in a fluid flow in our blood, how frequently is the glucose concentration going to change, right? It's not going to change every second, hopefully. And if it sort of stays on a 1 minute, 2 minute length scale, then you can take many, many samples. And in that case, you can improve the signal to noise ratio considerably, and you can detect very minute signal levels. And finally, if you consider the noise properly and analyze them properly, interpret them properly, and design the system accurately, only then you can expect a very good biosensor platform that will be useful and will not have significant amount of false positive or false negative associated with these noise sources. Okay, let me end here. In the next couple of lectures, we are going to bring everything together and then interpret everything that we have learned so far in terms of a genome sequencing problem. So until next time, take care.